professorship in 2006 by the Ministry of Education in the Department of Chemistry, University of Science and Technology of China. He is the leading division of nanomaterial and chemistry in Hebei National Laboratory. His research interests include bio-inspired synthesis. He had the 350 referred journal and publication published highly impact factor journal with citation about 19,589 and H index 75. Wow. He has 17 invited book chapters and 12 patents. He served as an associate professor, editor of for crystal engineering communication and material research bulletin. Among his recent awards include the second prize of National Natural Science Award awarded by the Chinese government, the Roy Somya Medal of the International Solvothermal and Hydrothermal Association, Chem Society Emerging Investigator Award, awardee of the Young Innovation Award of the Chinese Chemical Society, BASF, Germany. Could you please start, Prof?
Okay, thank you.
Thank you.
It's my great pleasure to spend my first visit to Saudi Arabia. So today, what I want to talk about is microscopic nanoparticles assemblies, integration, functionalization, and applications. So this slide showing where is my hometown, my city, Hefei, located here. So it's very near to Beijing or Shanghai. You can travel either by flight or by express train to my city very conveniently. So welcome your visit in the future. In 2010, we published a special issue to recognize our contribution from our university to material science and chemistry. This is the logo of our university. So we are very proud of that, and also we have a very beautiful yellow mountain. So here you will see many very unique pines. They are growing on the rocks, and also you can see the very unique peaks. Even though the mountains is not so high, but it's really one of the most beautiful mountains in the world. So welcome your visit. So our university is the only one university belongs to CAS, Chinese Academy of Sciences, and also this is the main campus of our university, and also we are proud of that. So we have two national laboratories. The first one is National Synchrotron Radiation Laboratory, and which was built in 1980s. So welcome, you can use a lot of beamlines here if you want to use a synchrotron radiation technique. And also we have another newly established laboratory called Hefei National Laboratory for Physical Science at the micro scale. So here is, I think this laboratory, national laboratory, is one of the 5 national laboratories in China up to now. So here is the outline of my talk today. I will talk about some research activities where we synthesize some very unique nanoscale building blocks. And we consider how to design a regional synthetic method or routes to synthesize a high quality no-dimensional nanoscale building blocks. And also we use these nanoparticles as the building blocks to self-assemble them into some microscopic assemblies in the form of either in the form of thin film or some bulk scale material, and to look at what's the new functionalities we can bring in. So as you know, in many years ago, I think 10 years ago, Science launched a special issue to emphasize the relationship between materials and biology. And also you will see a lot of people, they are working on this using the concept learned from nature to design some of new material system. And my lab, we are considering how to use some BIOS-inspired strategy with using some of polymers. They are containing some of functional groups which are quite similar to the biomolecules, such as you will see phosphate, the carboxy groups of amine groups, which they are positive charge or negative charge in the solution, so that they can interact with the growing crystal, because by the positive charge or negative charge, they can interact with some specific crystal facet. So this is a good strategy for you to control the shape of the nanocrystal which are growing in the solution. So I think 10 years ago, I collaborated with German colleagues. We designed one of the molecules. They are contain densely packed phosphate groups, because these groups will be a negative charge in the solution. When you mix some of inorganic ions, such as barium or cobalt or calciums in the solution, these kind of molecules can induce the formation of this very unique double helix. This is the helical structure with either left hand or right hand. If you look at the surface of this helical structure, you'll see this is, you can identify this rod-like nanocrystal. They are highly aligned along the actual direction, so that they can build up this micro-sized helical structures in the solution, and a very environmental friendly condition in the solution. So we propose this elongated nanocrystal. They can selectively, they can align along the actual direction. They can induce the helical structure for the inorganic system. And then we use this similar strategy to using these different kind of double hydrophilic block copolymers with different functionalities to control the shape of the biominerals, such as this calcium carbonate. We can synthesize this very uniform micro-sized calcium carbonate spheres, and also you can get these multi-layers of pancake structures, and you also can get this very unique, this is ring-like structure, micro-rings. So that means the polymers with a similar functionality as biomolecules, they can control the growth process of this very different inorganic material. So then we consider how we can build up. How to build up these big guys. This is lacquer, is a seashell. Is it possible? But the answer may be yes, but because this lacquer-like structure, seashell structure is a multi-layer structure with a very unique, you can see the multi-layer structure. So in the chemistry lab, we apply the freezing drying technique to get these multi-layers polymeric structures. Then we do some chemistry here. Then we grow calcium carbonate within these multi-layer structures. Then finally, indeed, we can get this microscopic sized biomimetic seashell structure. Here is the calcium carbonate. You will see here our real samples. If you look at the mechanical performance, indeed, our material is very near the original seashell, the mechanical properties. And also, we apply the different strategy. We mix the nanoplasts with the polymers. Then we can cast them into the nacromimic film. Then we introduce some polymers here. Then you can hot press them. Finally, indeed, we can get these bigger layer structures, which are quite similar to the seashell. So then here I have one video to showing the comparison between our artificial lacquer with some of original lacquer. Here you will see original lacquer is very easy to break. But for our material, artificial ones, you will see the under impact test, you will see very tough, and you can't break it for our artificial material. So this is the example showing indeed the microscopic sized assemblies. If you combine the nano building blocks with some polymers to indeed you can get some very tough material. Now what I want to talk about today is nanoparticle assemblies, because this is the emerging research field is quite hot now, because people, they prefer to align these log-like nanorods into raft-like structure, the assembly, because you see the raft-like assembly, they have a different functionality as the individual logs which are floating on the river, right? If you make them align, then it's possible to get some microscopic size assemblies, assembled structure. Just like DNA molecules, if you look at it, if we have very nanowires with very thin nanowires, they have a higher aspect ratio, then they have almost similar behavior in the solution. They can either folding, either using, nowadays you can use a DNA molecule to construct many assembled structures. In any shape, any structure, you can do programmed assembly, you can do many things. So why we not choose these ultra-thin nanowires as building blocks in the future for the device fabrication for many applications in the future? So before talking that, I just emphasize some of the significant impact for the nanostructure, because they have a nanostructure very small, they have a huge surface area, so they have a poor stability, but they showing higher reactivity. So this is a good thing for us, because we can take advantage of this high reactivity of a nanostructure material. You can do structure transformation, you can do chemical transformation, you can do ionic exchange reaction, so you can do many things. Even you can use these ultra-thin nanowires as a template to guide our synthesis. I will talk something about that to make this approach very useful for you to access different kind of material, one-dimensional material. So, so stability of the nanocrystal is a big problem for their application. For example, copper nanowires, they are very easy to be oxidized if you store in the backer, if you very isolated with oxygen. So small amount of oxygen even can make them oxidized totally. So that's a way, even for quantum dots. So their stability is a big issue in the future. So in my group many years ago, we found that these tellurium nanowires, elemental tellurium nanowires, you will see very beautiful structures, high aspect ratio, very narrow diameter, but if you store them in the encelor or water solution, you will see few hours later or several days later, it will totally disappear because they are oxidized. Because these guys are very reactive, right? So very easy. Then we study, because tellurium elements is a very key material for clean energy in future. If you look at the DOE book, the critical material strategy, they list tellurium elements as one of the 16 key material in the future, because these elements is very, very important in future. So that's the reason why we choose this system. Then we study the oxidation kinetics for these ultra-thin nanowires. So we carefully study this oxidation process. Then finally we can calculate the apparent activation energy for this oxidation reaction. You will see the number, the activation energy is really very low. That indicates these ultra-thin nanowires, because they have very thin diameter and huge surface area, they are very easy to be oxidized even under ambient condition. So that is how we can store these high quality nanowires in the solution. If you store in the water, if you close this cap, you keep it isolated with oxygen, you will find that you still can't store them totally oxidized, right? But if you store them in the reducing atmosphere, you keep them longer. So you can keep it even more than 1 month. So that's the indication that this kind of structure, we still can store them if you choose a different storage method. So because this ultra-thin nanowire are very easy to be oxidized, right? Nowadays we synthesize these tellurium nanowires from ionic species. Now we can do recycling. Later on, I will show some of example. So now I show you what we can do with these ultra-thin nanowires. Because we can use these ultra-thin nanowires to synthesize many things. We use this ultra-thin nanowire as a template. You can do some of many reactions. You will see here the example. Because these telluride nanowires are very reactive, they almost can react with many metal species, ionic metal species. For example, if they meet cadmium chloride, they can chemically transfer them into cadmium telluride nanowire. This is a topological transformation process, right? If you mix with silver nitride, you will see can chemically transfer them into silver telluride. If you mix with that ionic net species, then they can chemically transfer them into semiconductor nanowires. You can do many things. Even you can mix with gold acid or even palladium chloride. You can transfer them into palladium nanowires or nanotubes. Many different systems you can try. Now we can synthesize this ultra-thin telluride nanowire in huge amount. We can do such a reaction in the reactors with 10 liter, so that you can one part synthesis. You can get a kilogram of these high quality nanowires. Now you can do, you will see, you will check the morphology of this nanowire. Why high quality is really very good. So now if we further to coating the telluride nanowires with the cerium. Cerium is also they are sitting at the same groups. So that you can do these, you can get these core shell nanowires. Coupled with cerium elements, then we find that this kind of material, this new nanostructure, they are also very reactive. They almost can react with many things, so that you can get different kind of metal telluride or metal cellulite, and also metal telluronic material nanowires in huge amounts, and also different system. So that you can access the good things is that you can get this nanowires with different composition of components. So now we can synthesize, I think, the alloyed hybrid core shell nanowires. I think it's more than 45 kinds of these inorganic nanowires with high quality. So due to time limitation, I don't have time to address more about the mechanism, but the synthesis indeed the high efficiency is very versatile. Then we do another chemical reaction. We use these telluride nanowires. We do hydrothermal carbonization. You can make a starch to be carbonized in the solution on the surface of these telluride nanowires. Then you can do further. You can exchange a reaction. You mix with palladium, ionic palladium species. You can transfer them these telluride elements into platinum. Platinum is a good catalyst, right? So that you can cast them into the thin film. If you remove the carbon species on the surface of these palladium nanowires, you can get freestanding palladium nanowires network in a thin film and in microscopic size. And we studied their electrocatalytic performance for the oxygen reduction reaction. You will show the result showing indeed you can improve. You can find that the palladium nanowires network is a good. They are showing good stability for the oxygen reduction reaction after many times of CV cycles. And another way you can get new nanowires, alloyed nanowires. You can tune the palladium composition so that you can optimize this electrocatalytic performance for this alloyed nanowire system. Even you can coating palladium, very thin palladium layers on the surface of palladium nanowires so that you can further engineering their electrocatalytic performance. So there are many ways for you to synthesize the new nanowires. So this is a good Then we want to use these tera nanowires to get carbon nanofibers. So we do the hydrothermal carbonization on the surface of these tera nanowires. If you remove this tera nanowire, you can get this huge size hydrogel or aerogel if you remove water. So this is the carbon nanofibers in any size, from 1 centimeter high to 20 centimeter high. So you really get a very big nanowire network. So this kind of material is very useful because this is the carbon. Because carbon is a good, excellent absorbent, and even for doping for the design new material. So one application of this our carbon nanofibers is that if you remove this tellurium nanowire, you see black stuff here. If you remove it, etching it, then you can get a carbon fiber. You can cast them into memory. This memory is a different. Is a microscopic size. You can quite flexible, and because these fibers they have a different diameter, so that you can get the memory with a different porosity. So for the filtration application, we can use our hydrophilic the fibers memory as a filter. You can separate nanoparticles with different size using such a memory, because this memory have a different porosity. So here some data showing indeed you can do this filtration application. You can separate nanoparticle with a different size in the range of few nanometer to 100 nanometer. So, and also filtration is very good, very fast. Then the issue is question that can we recycle this template? Because we synthesize tellurium nanowires just from the sodium of the ionic tellurium species. So we use this, we synthesize from these ionic species into nanowires. We use them as a physical template or chemical template. After that, if you etch them, you can collect these ionic species again. But you can do this recycling process. So some of the data showing indeed look very promising to recycle these tellurium nanowires in the chemical synthetic system, so that you can reduce the cost for you to use this kind of nanowire templates in the future. Here is some data showing recycled nanowires. Indeed, they still keep a very good quality. They have a high aspect ratio, and also their diameter is very uniform. So this is a good way for you. We start from these tellurium nanowires, which we can scale up synthesis, and then you can do many things. You can do chemical transformation. You can use them as a physical template. You can access different kind of nanowire system, so that you can do this scale up synthesis. You can get a very giant nanowire network in the future. So this material is a nanowire. Yes, it's very small. You can't see it by your eye, but you can use them as a templating strategy. You can use them to synthesize different nanowire system. And then you can use the nanowire to construct some microscopic size in the form of thin film, or even some in the three-dimensional hydrogel or aerogel system. So, and with a very good flexibility, and you can further engineering the surface for the different application in the future. For one-dimensional nanowires or nanoribbons is another strategy that you can modify the surface. This is a nanoribbon. This is called cobalt selenide, which we discovered in 2009. You can see it's a very ultra-thin nanowires. If you are nanoribbon, if you look at the thickness direction, you can identify the well-defined few layers. This is cobalt selenide slabs, isolated, separated with a monolayer of amine molecules in this very new system. Then we use them as a matrix. You can marry this nanoribbon with a different material, so you can bring in new material on the surface of this nanoribbon, so that you can get many kinds of nanocomposite materials, which are showing promising to access a new electrocatalysis system in the future. Now, how we can get these nanowires to become ordered? So I will show some data. We use these nanowires as a building block. You can get a nanowire thin film. And the strategy is very easy. We're using the traditional non-gamma budget technique. You float this hydrophilic nanowire on the surface of air and solid. Then you apply substitution. You make these nanowires highly aligned or along the same direction so that you can get monolayer nanowires, thin film. You can deposit the second layer with a different tuning angle. You can construct a different nanowire system, thin film, with a different layer number, so that and also you can use small X-ray to identify this order structure after you assemble them into an ordered nanowire. Here's some data showing two layers with a different tuning angle. You will get this mesh-like nanowire network. This is the two layers. But of course, you can do third, fourth, and different nanowire, so that you can get a nanowire thin film with a different tunable thickness, right? So we use them for the photoconductivity application. We can use this huge size nanowire thin film to construct nano device for the photoconductivity. You can identify this layer number dependent electron current generated by this nanowire assembled system. And again, you can use these highly reactive tellurium nanowires as a substrate. You can react partially with a different system. You can chemically transform them into different hetero nanowire thin film, so that you can further engineering their photoconductivity in the future. And also how we can use this nanowire to make the solid surface become conductive. So this is difficult really, but we can do this way. We coating the surface. We use our nanowire, highly oriented nanowire assembled structure. You deposit the nanowire ultra thin film onto the flexible substrate, almost transparent. You can deposit in the gold acid for a few minutes. You will see these black dots sitting on the tellurium nanowires, because our tellurium nanowires very reactive, right? So that you can get this hybrid system. Then you can identify this gold appearance, gold nanoparticle sitting on this backbone of the nanowires, so that you can tune their conductivity. So one system is that we can use our nanowires as a thin film to use them as a flexible substrate, flexible electrodes. You will see here some data showing after many times of bending cycles, they can still keep the excellent conductivity for you to use this nanowire coating to make any surface become conductive in the future. Even you can control the transmission efficiency for the light, right? So even sometimes you can get a transparent flexible electrode. Here some data is showing if you have a huge area, you can make a huge area become conductive. You can use our nanowire assembled system to light up to make the surface become conductive. Now we think about how to make a more stable material. We use the silver nanowires. We mix the silver nanowires together with our tellurium ultra-thin nanowires. You can make a nanowire network system. After etching the tellurium nanowires, then you leave this silver nanowire network here, so that you can get a totally transparent silver nanowires network. Very thin, and they are highly transparent. So then you can get quite flexible. Even you bending this thin film for many times, more than 300 bending cycles, you can keep excellent conductivity for the silver nanowire network. So that you can reuse them, if you use them to replace the ITO, the substrate, then indeed you can use our nanowire system for the touch screen application, for the flexible nano device in the future. And many things, nanowire network, even we can use this nanowire network to make transparent, flexible electrodes, or even you can printing these nanowires assembled structure on the large size substrate. You can do many things. This is the chrome for the electrochromatic application. So, and then later on we introduce solvent A and solvent B, which is not insoluble with each other. So, but the interface will be here. Then you can introduce this interfacial assembly strategy. You can make a different kind of a nano structure become thin film, and even you can co-assemble this nano crystal with our nanowires. You can make a different nanowire hybrid system. So this is indicate this interfacial assembly strategy is quite general for you to self-assembly this different nanoscale building blocks in the future. And lastly, I show you we're using these nanowires. Even you can coating A4 papers. You can make your A4 papers become conductive. Even you can use this substrate for the very reliable device application. You will see some data is really very promising. So the concept is very easy to make this disordered nanowire become ordered. Because if you get ordered nanowires, then you can get different thin film with a different hierarchical structure than for the further for the device fabrication in the future. That's in compared to the individual nanowires. Nanowires assemble structure is more reliable for the nano device fabrication in the future. So to make one example, I show you this is the silver nanowires. We make this silver nanowire become ordered. Then later on, we find that compared with the disordered nanowires, silver nanowire assembled structure, thin film, which we use a very simple deep coating strategy. You will see this randomly aligned nanowires. You will see the transmission efficiency. You can't find this polarized angle dependent this transmission efficiency. If you get all the structure much better, you can the light shining with a different polarized angle on the surface of the silver nanowires, other than the silver nanowires. You can tune the transmission efficiency. This is the example demonstrate is indeed assemble all the nanowire structure is much better for you to further control the property. Then we use small angle X-ray to identify the kinetics for the assembly of the ultra-thin nanowires on the surface. We use synchrotron radiation technique to monitor the self-assemble process of this ultra-thin nanowire on the surface of air and the solvent surface. So you can identify the time-dependent evolution of these nanowires during the ordering process, right? So really can identify this in the small angle X-ray. You can identify this accompanying the ordered structure formation. You can identify this ordered structure. So we propose that we can use nanowires as a building block. You can make a nanowire thin film. You can make a different hybrid or hetero nanowire system. You can further engineering. You can do many things in the future. So for the nanowires assemble structure for the application in the future. And lastly, I talk about three-dimensional nanowire network. So here is my student where he will come back China this end of this year. Is work with Klaus Mullen in Mainz. He work on we use the parallel nanowire as a template. We use this so-called microscopic scale template synthesize so that we can synthesize this carbon nanofibers of hydrogel or aerogel. We start from 75 milliliter. Now we can go to 12 liter. 12 liter is a really big one. So this even we can go to 20 liter. You can get the 20 liter nanowires. That means the microscopic synthesize scale synthesis is indeed possible. So far, and really this nanowires network, really big guys, right? So that's good for the future application for the different material system. So we use this carbon nanofibers network sponge. We call it the nanofiber sponge. You will see the network. You soak in toxic molecules with polluted by dye molecules. Then you can use screening. You can get fresh water. Yeah, clean water. You can use our this lightning weight nanowire network to use them to absorb different kind of hydrocarbons with a density lighter than in water. So you can even you can burn some toxic molecules after you use. You can recycle these carbon fibers in the future for the different application. A good thing is that you can scrap synthesis, so you can get any size. So this is good in the future for the application. And
2 minutes.
Okay, so I have to quickly. So here we again use the pure nanowires to guide our synthesis. You can glue morphs on the surface of this pure nanowire. You remove purium, then you can get the morph fibers. You can further heat treatment. You can get these porous carbon fibers in the with huge surface area for the new. This is mesoporous carbon fibers. I think finally I should stop here. And again, we use these different nanowires for the functionalize some micro scale object. You can make our three-dimensional the sponge which you use in kitchen room. In kitchen room, they are not conductive, but if you assemble our one-dimensional nanowires network within this highly porous structure, you can make them become conductive, right? And also you can use them to make sponge, three-dimensional sponge become functionalized. We can use them for the pressure sensor application in the future, and many things. So after you scale up, synthesize nano building blocks, you can do many things for the many pressure application in the future. So finally I should thanks the organizer give me this chance, and I look forward to your questions.
Thank you, Professor. Thank you, Prof.
Yes.
Any question from the mail section?
What? Pardon?
Any question from the mail section?
Yeah.
Yeah, for some application like preparation of thin film or
Sorry, we can't hear the question.
Yeah, question.
Yes, microphone. You need a microphone here. Do you have microphone?
Professor Chen, could you come forward for the mic?
Yes.
Yes.
so the question is about why you specifically choose this nanowire. Sometimes other type of nano material like a square, maybe
Yes.
sphere,
Yes.
maybe even more suitable for
Yes.
preparation of thin film
Yes.
or membrane. So
Yeah, this
I
is
wonder if any other study.
Very good question. So that's the reason why we choose ultra-thin nanowires with high aspect ratio and tunable diameter. But the good thing is that we use this very tiny stuff. We want to introduce the huge surface area, and we want our ultra-thin nanowire become more reactive so that you can access different kind of material. That's one issue. And another issue is that the one-dimensional structure is a good stuff for you to make assembled structure, compared with zero dots or some cubics or some other material. Because they have a huge surface area and also very thin thickness. So that's another consideration choice.
Any more questions from the mail section? Any question from the female section? Thank you very much, Prof. Yo. Let's give Prof. Yo a hand of applause.
Thank you.
اثنين
ها؟
لا غرفة كام؟ مش عارف اثنين
لا هنا شبكة كده الصوت يمشي. بسم الله الرحمن الرحيم. لا خلاص
السلام عليكم. هذا العرض خلاص. Next we will present Prof. Muhammad Al-Qasim Muhammad Hassouna. His talk will be about absorptive removal of iron and manganese from groundwater using carbon nanotube clay composite and organic clay nanocomposite. Please go.
Thank you, Mr. President. I would like first of all to express my thanks and appreciation for the organizing committee for the effort done. I have been given the code number 211 before, but I don't know, it has been changed to 28, never mind. Our subject, absorptive removal of iron manganese from groundwater using carbon nanotubes, clay composite and organic clay non-composite. This work has been done as a case study in Beni Suef Governorate, which lies about 124 to the south of Cairo, the capital of Egypt. The town El-Wasta, which is about 30 kilometers to the north of Beni Suef. The drinking water is a mixture of Nile water and some ground water wells. It has been found that this well has been stopped for consumption because both the percentage of iron and manganese have exceeded the permissible limits completely. Iron and manganese are the most common elements in the ground supplies. Iron is the most frequent of these two contaminants, but they often exist together. Iron and manganese are more common in deeper wells where the water has been in contact with the rocks for a long time. EPA determines the maximum contamination levels for iron and manganese by 0.3 milligram per liter and 0.4 milligram per liter respectively due to their health effects. Iron and manganese are the most common elements. Okay, it has been repeated. Yes, sorry. Sorry. Mhm. Adsorption process is arguably one of the most popular methods for removal because of its simplicity, convenience, and efficiency. Clays have a high adsorption capacity due to their lamellar structure, which provides high specific surface areas, and possibly due to adsorbed ions and the polar organic molecules on particle external site and in interlayer positions. Starch is a promising raw material because of its annual availability from many plants and low cost. Carbon nanotubes, which are the graphite sheets rolled over into the cylinder tube material, have been an attractive material for its specific mechanical, physical, chemical, electroconductive, and field emission properties. The comparison of carbon nanotubes with other adsorbents suggests that the carbon nanotubes have significant potential applications in environmental. The single-walled and the multi-walled carbon nanotubes are synthesized by thermal chemical vapor deposition, CVD method. Kaolin clay was collected from kilometer number 18 in the eastern Armenia Beniswave Road. Iron and manganese certified reference materials are provided by MRNG. The first stage of this work, we have examined the effect of crude kaolin on the removal process of the for iron and manganese. It has achieved about 40–45% removal after acid modification with acetic acid, sulfuric acid, citric acid. These modifications have achieved about up to 70% removal of both metal ions. This work has been published, as you see, but the present work aimed at increasing the removal efficiency through the formation of organocomposites using starch, first of all, then developing the method through the use of carbon nanotubes, clay composite, which has achieved the best removal up to 99% for both elements. Instrumentation, the morphology of the prepared samples and composite were investigated using scanning electron microscopes, and iron and manganese analyses were carried out using inductively coupled plasma atomic emission spectroscopy. Jar test for stirrer was used for constant stirring of the sample. X-ray diffractometer was used to investigate the phase structure of the investigated samples. Sampling. Water samples were collected in polyethylene containers, 10 liters capacities. The sample container was washed with dilute nitric acid and rinsed with distilled water. The samples were preserved immediately after sampling by acidifying with concentrated nitric acid to pH lower than 2, then stored in a refrigerator at approximately 4 centigrade to prevent change in volume due to evaporation. The organocomposite preparation, starch, clay, nanocomposite, was prepared taking 5 grams of the clay, which are dispersed in 100 milliliter boiling distilled water for 5 minutes. The starch solution, which is 5 grams starch dissolved in cold distilled water, was added dropwisely to the clay suspension The suspension was heated for 3 minutes with continuous stirring. The solution was then poured by decantation, and then the composite was transferred to crucible. The composite was dried in an oven at 110 centigrade for 24 hours, and then it was milled to the specific nano size. Carbon nanotubes clay preparation, as we referred before, has been prepared during here. The clay, kaolin, was used as a catalyst during the synthesis of carbon nanotubes using the chemical vapor deposition technique. Synthesis of carbon nanotubes was carried out in reactor employing the double bias assisted hot filament chemical vapor deposition method. The process time was 30 minutes. Characterization of kaolin clay and its modified forms, structures and morphologies of natural kaolin and organic clay composite were studied by X-ray diffraction, XRD, scanning electron microscope, SM, CCM, and TEM, transmission electron microscope. The structural characterization of the organocomposite, starch composite, and carbon nanotubes clay composite were performed by XRD with a wavelength 1.54 angstrom in the diffraction angle ranging from 5 to 80 degrees. Here is the figure of the XRD pattern of starch clay composite. The results indicate that carbon nanotubes, clay, composite, I think one before. Okay, the sequence, okay. The results indicate that carbon nanotubes clay composite is successfully fabricated, and the clay or the carbon nanotubes are not exfoliation to each other. Here is the XRD pattern of carbon nanotubes clay composite. The interpretation of such structures depending upon the disappearance of the parent peaks and the appearance of new ones, so that the new composite has been elucidated. Top view thin micrograph of the starch kaolin composite is shown in figure. It shows that the homogeneity in the composite surface, this may be attributed to the high adhesion between the two components. For this sake, starch has been selected. The morphology of multi-wall carbon nanotubes, kaolin clay composite, was characterized by transmission electron microscope. Then, figure shows the tubular structure of multi-wall carbon nanotubes. In addition, the figure shows the kaolin composite. This is the 10 images for carbon nanotubes. It is one of in the paper we have about 10 figures from different sides, from different angles. This is one for two. It is a very concise presentation. Absorption of metal ions, effect of adsorbent. We have studied different parameters which relates or deals with the improvement of the percentage of removal. First of all, the effect of adsorbent dosage. The absorption study was carried out using the organocomposite, starch composite, and the carbon nanotubes clay. one as adsorbents. The effect of different doses of them on the removal efficiency of iron and manganese from non-standards and the ground authentic samples, of course, first of all, then has been applied directly on the real samples, which are groundwater samples. The doses of carbon nanotubes clay as representative, the removal percentage of iron from standard solution, the A using carbon nanotubes, B A carbon nanotubes clay, and B starch. It is clear that the increase
2 minutes.
Yes. From the paper says that the absorption efficiency increases with the increase of the dose. This increase may be ascribed to an increase in the surface area. Logic increase, effect of contact time, as you see, the figures also with time, this is increase. Effect of the pH on the absorption is process. You see the pH range has been almost stable, almost horizontal after 6 value, pH value. Effect of temperature, the absorption of iron and manganese in solution was found to decrease with an increase in temperature in case of organic composite, while in case of carbon nanotubes, absorption of iron and manganese in solutions was found to increase with an increase in temperature as shown in figures. Thermodynamics of the absorption, thermodynamics can be determined using the equilibrium constants, so on, delta G, delta H. The data are graphically represented in figure. I think this is the last one. Thermodynamic parameters for removal of iron using starch clay composite. This table illustrates the thermodynamic parameters for the absorption process for different equations for both manganese and iron using the adsorbents used. Absorption models, we have the Langmuir and the Freundlich are most frequently. We have applied both of them. Langmuir isotherm, the model supposes that absorption takes place at a specific surface with a single coating layer on this surface. It estimates the maximum monolayer absorption capacity of the absorbent and also decides whether the process is taking place as monolayer absorption. Freundlich, and thanks for all of you.
Thank you, Dr. Any question from the male side, please? Any question from the female side? Thank you very much, Mr. Muhammad, for the interesting talk, and please give another round of applause.
So your material is after you adsorb, remove iron or manganese, is it possible to recycle?
Okay, desorption process is being in subsequent work.
So how many times you can recycle?
No. We started to go on. We have achieved sorption first of all, and desorption will be in the subsequent stage.
Okay. Thank you.
But it is planned. It is planned. Yeah. It is in our mind.
When you make the ion exchange, what is the rate of water that you flow? So how fast can you do the ion exchange? Because the problem is that you need to treat the water very fast in order to have some application.
Ion exchange is another thing. We are using adsorbents absorbed materials, mainly clay material. We have started the study with clay crudely, without any
So
treatment.
it's not continuous flow. Your experiments are made on a batch. So you stir the clay.
Yes.
And
This
for
is
how
a
long?
systematic study.
And
We
for how long?
batch experiments, then application, then recommendation for the volume, total volume of a basin for drinking water, and so on. But in the laboratory, we are applying the methods on a batches. Certainly.
And can you tell me the pH of the exchange?
I haven't do ion exchange, my dear. Here we are dealing with an absorption process. The advantage here that we use the very cheap, no cheap, priceless. It is a clay from the land. It has achieved, first of all, from 40 to 45% removal. But after modification with acid, it achieved about 70. This subsequent, or this present study, we have reached 99%, but using loading with carbon nanotube composite. I hope that I answered. Shukran.
Thank you very much, Prof. Muhammad.
Thank you.
Thank you.
الله يبارك فيك. لا الحقنة جابت نتيجة.
لقيت الشنطة ولا لا؟
لا مش لاقيها.
فيها حاجة يعني مهمة؟
فيها الوصل وفيها البحث ده. هارد كوبي منه.
يعني خبر مش فاهم بحث
أنا مش عارف وفيها الكروت بتاعته.
هو خدها غلط.
هذا الشنطة
ما هي خدها غلط.
خدها غلط.
يعني بقى إيه بس
هو لو فتحها ويعرف
لو فتحها
وفيها السي دي بتاعتي يعني أنا محدش قدمني ولا حد سأل فيا.
Our next oral talk will be represented by the researcher Huda Farouk Ahmed Muhammad Zafran instead of Prof. Sahar Muhammad, and the representation will be about agricultural drainage water treatment using artificial neutral network.
Bismillahirrahmanirrahim. First of all, I would like to express my feelings that I am very happy to share at this huge conference. Thanks for organizing committee. Let me start our seminar today, which is talking about agricultural drainage water treatment using artificial neural network. It is a review. It is an honor for me to share my partner, Dr. Mahmoud Nasr. He is a lecturer at Sanitary Engineering Department, Faculty of Engineering at Zagreb University. First, what is meant by drainage? Drainage is the natural or artificial removal of surface and subsurface water from an area. And agricultural drainage water is a natural or artificial removal of surface and subsurface water from an agricultural area. The benefits of drainage can be summarized as follows. Drainage promotes beneficial soil bacteria activity and improves soil tilth. There is less surface runoff. There is less surface runoff and soil erosion on drained land. Improved field machine traffic, ability to reduce soil structure damage, soil compaction, is reduced and less energy is required for field machine operations. Crop yields are increased because of improved water management and uptake of plant nutrients. Higher value crops can be planted, and there is flexibility to introduce new and improved cropping system. In general, land value and productivity are increased. Farm income is increased, and income variability reduced. Drainage maintains favorable soil and air environments in the crop root zone. Types of drainage system. We have two types, surface drainage and subsurface drainage. About surface drainage is often achieved by land forming and smoothing to remove isolated depression or by constructing parallel ditches. But subsurface drainage, these deep ditches or subsurface pipe drainage systems enable a more rapid water table drawn down. Because of irrigation process contains chemical compounds like synthetic fertilizer, compost, manures, and biosolids. Agricultural drainage water could be loaded with several constituents of chemical pollutants. They may be organic contaminants like organic chlorine, pesticides, or inorganic contaminants like nitrogen and phosphorus compounds. Both organic and inorganic contaminants need adequate optimization of management between aerobic anoxic treatment process. Actually, agricultural drainage water treatment techniques could be divided into chemical, physical, and biological treatments techniques. Let me talk about what is meant by artificial intelligence technique. It is technique that mimics the operation of the human brain, nerves, and neurons, and comprise of densely interconnected computer process working simultaneously in parallel. A feature of neural networks is that they are programmed to learn by sifting data repeatedly, looking for relationships to build mathematical models and automatically correcting these models to refine them continuously, and also called artificial neural network, ANN. Can be used for modeling such treatment processes. It can be used for better prediction for the process performance owing to their high accuracy, adequacy, and quite promising applications in engineering. Moreover, ANN is capable of detecting the interactive influence between variables as well as their correlation with the simulation output. This would minimize the operation cost and assess the stability of environmental balance. Artificial neural network, which is computational model based on the structure and functions of biological neural networks. Followed through the network affects the structure of the ANN because a neural network changes or learns in a sense based on that input and output. As you can see, we have some layers in the left side in red color, and some circles in yellow color, and the hidden circles or layers in blue color. That an artificial neural network is an interconnected group of nodes akin to the vast network of neurons in a brain, where each circle node represents an artificial neuron and an arrow represents a connection from the output of one neuron to the input of another. At last, ANNS are considered non-linear statistical data modeling tools where the complex relationships between inputs and outputs are modeled or patterns are found. Did we talk about the applications of artificial neural network? Simply, artificial intelligence is the technique that can control plant operations in a proactive way. Artificial neural network can be used for modeling such treatment process. It can be used for better prediction of the process performance owing to their high accuracy, efficacy, and quite promising applications in engineering. This would minimize the operation costs and assess the stability of environmental balance. Moreover, it is capable of depicting the interactive influence between variables as well as their correlation with the simulation output. Class, thank you for your attention. Thank you. Any questions from the male side? Any question?
No.
Any question from the female side?
Hello? Any question from the men's side? The female side? Thank you very much. Thank you very much, Dr. Sa.